Okay, we can start. So welcome everybody to this week's Majorana-Raychaudhuri seminar series. We have two speakers today. First is Ahmed from University in Czechia and Brac University, Bangladesh, and he's going to talk about back to the origins of brane-antibrane inflation. So let us begin. I will send you a reminder when 5 minutes are left.
Okay. Okay. Thank you so much for the invitation to speak here. I will use a timer myself so that I don't go over time. Okay. So thank you for the opportunity to speak here. This work was done in collaboration with few collaborators from Bologna, Michele Ciccoli, Francesco Marino from the University of Cambridge. We had Fernando Quevedo, Gonzalo Villa, Mario Ramos Hamud, and Chris Hughes, and myself. So with this, this is the brief outline of the talk that I will be giving. So let me first try to motivate why we're looking at this specific scenario, which I think now it's more than 20 years old. So there are some motivations, which I call motivations from the past. As we know, the standard problems of standard Big Bang cosmology require an early period of accelerated expansion, which we call inflation. So at the current stage of our cosmological storytelling, we are in an era driven by dark energy. We are in a dark energy dominated era where you have the expansion of space and time, which is again accelerating. So we need realistic scenarios where constraints from experiments is satisfied and we can complete our cosmological storytelling we have been trying to complete, starting from the very early universe to the universe now. But as it turns out, dealing with them most of the time signals a naive breakdown of the effective field theory analysis. If you are in favor of the dark energy being explained by the cosmological constant has effective field theory problems like radiative instability and the issue of fine tuning. For the case of inflation, you have many times higher dimensional operators ruining the validity of your effective field theory. So it signals that we really need a quantum theory of gravity to address these problems. And our favorite one for this is string theory. So string theory is a framework of quantum gravity, which provides a framework for studying gravity and quantum mechanics in a consistent fashion. So what are our motivations now? Our motivations now is that experimentally favored scenarios for inflationary potentials are of this form. So in string theory, the famous example is the case of brane-antibrane inflation, which is of the first kind, an example of the first kind. So, but as it turns out, in the early 2000s, the famous paper by Patruka Losh, Liam McAllister, Maldacena Trivedi pointed out in their KKLMMP paper that this brane-antibrane inflationary scenario suffers from eta problem, that is the slow roll parameter becoming order 1 after you're done with the moduli stabilization. So moduli fields are basically free scalar fields in string theory, which needs to have a potential to avoid problems, phenomenological problems like fifth forces and so on. So it turns out without moduli stabilization or without, in the original case, it was hard to get inflation in a finite region of compact space. Specifically, since string theory is a theory which has higher dimensions, which we call LKK, which is the length or the scale of the extra dimensions, the eta parameter goes as LKK over R. So where R is the distance or the separation between a brane and an antibrane, which is our proposed inflaton candidate. So as you can see, we need eta to be much less than 1, but it turns out you need, for eta to be much less than 1, you need the branes to be separated by a distance more than the distance of the extra dimension, which is a contradiction. And on top of that, there's another motivation, which I list as motivations now, is that perturbative moduli stabilization, we will see what it means a bit in detail, can solve the problem. And it turns out why now? Because after 20 years of this KKLMMT paper, we now know more corrections in string theory, which are alpha prime and GS corrections, which we'll see again. And we know how to compute them.
Ah, yes, we have to hang. But we want to hang it like this because I saw downstairs that for these files they have this kind of frame in a way.
Okay, yeah. So it turns out that perturbative moduli stabilization can solve the problem. And on top of that, do you have a scenario when you have your effective field theory under control? And it turns out all are positive from our results, which I will now explain. So what is brane-antibrane inflation? So you have a brane and an antibrane where the distance between the two or the separation between the two serves as an inflaton candidate. So the potential is again of the experimentally favored form where you have like a Coulomb structure 1/5⁴, as you can see from here. So with that, as we'll see in the discussion, in the upcoming discussions, that it was very hard to get inflation in a compact set without stabilizing the volume modulus, which is a modulus corresponding to the volume of the extra dimensions. And it turns out the late time physics or the physics of after inflation ended or when we are in an era of dark energy is super important for this analysis because you have to stabilize or generate a potential for the volume mode.
Sorry, can I ask a question?
Yeah.
Why do you say that this is Coulomb form? I don't understand now how this C0 is related to Coulomb.
For Coulomb, you have the inverse potentials, right? Coulomb like that. Okay, maybe I should be a bit better with my wording.
So, what is the physical origin of this constant term in this scenario, even forgetting Coulomb?
Okay. The first term is, I'll show the derivation a bit later. The first term is actually coming from the tension, or if you, for example, if you have, if you write the action, the dBi action, the Chern-Simons term for the anti-brane, both of them add up. So you have 2 times the tension of the brane, which is the first term.
Okay, thank you. Yes, I understand.
Yeah. Okay.
Thank you.
Yeah. Okay. Thank you so much. Okay. So in string theory, there are 2 kinds of perturbative corrections, which are the alpha prime and GS corrections. And alpha prime corrections are like higher derivative corrections, and GS are string loop corrections. And when I say higher derivative, it's like, for example, if we have seen the Einstein-Hilbert term, so a term in alpha prime, higher order in alpha prime, let's say alpha prime square correction would go as Riemann, or Ricci to the square or R squared term. These are higher derivatives in the metric. So this gives correction to the 4D effective action upon compactification, which we'll see. And upon using these corrections, we can construct 4-dimensional supersymmetric ingredients like the scalar potential and the F-term scalar potential, which we will see helps us stabilize the volume modulus or the scalar modulus. So yeah, let's see the example. So the 4D n equal to 1 supergravity is described by the scalar potential and the superpotential. From supersymmetric renormalization theorems, we know that the scalar potential receives both perturbative and non-perturbative corrections, and the superpotential only receives non-perturbative corrections. So with this, we can construct the F-term scalar potential, which is a sum over all the moduli in the field. In this compactification, you have S, which denotes the dilaton or the axiodilaton, U, the complex structure moduli, and Ij, the scalar modulus. The complex structure tells us about the shape of the extra dimensions, and the scalar modulus Ij tells us about the size or the volume of the extra dimensions. So as I've been saying, this moduli needs to be stabilized, otherwise we run into phenomenological issues. So one can check that at tree level, that is without using the perturbative and non-perturbative corrections that I've listed in 3 and 4, the Kähler modulus is unfixed. That is, the potential is flat. So what is the way out? The way out to stabilize the Kähler modulus is to consider perturbative or non-perturbative correction. So two of the famous results are the KKLT scenario, where they use non-perturbative corrections to the superpotential to generate a minima for the Kähler modulus, or to generate a potential for the Kähler modulus. And for the large volume scenario, which it uses a combination of non-perturbative corrections and perturbative corrections to generate potential for the Kähler modulus or Kähler moduli. So in terms of perturbative corrections for LVS uses the first alpha prime correction in type 2b string theory, which is at order alpha prime cube, and Riemann to the fourth. That's a Riemann to the fourth correction, and generates a potential. So this is another correction that we would also be using in our analysis. So since I'll show very quickly how if non-perturbative effects introduce eta problem for the brane-antibrane inflaton. So non-perturbative effects introduce an eta problem. So in this analysis of late time
Sorry,
physics.
can I ask one question? Sorry.
Yeah, sure.
Yes. What type of non-perturbative effects can you add to the Kähler potential?
I'm actually not aware of this. Most analysis, for example,
Yeah,
KKLT and
because
LBS.
I think,
Yeah.
I mean, correct me if I'm wrong, because I think you cannot add non-perturbative effects to the Kähler potential, right? Because it will make the potential imaginary. The Kähler potential has to be real.
I'm not.
Maybe we can
sure
discuss
about.
later. Yeah, go ahead.
Yeah. I think you can. Okay, yeah, I'm not sure
We can
about this,
discuss
but
later. Yeah, we can discuss
okay.
later. Yeah.
Thank you for the question. So usually in KKLT and LVS, we use non-perturbative effects to the superpotential, which helps us generate the minimum.
Yes, thank you.
Yeah. So non-perturbative effects, since introduce a problem for the inflaton, we can use perturbative corrections to fix the Kähler modulus. The leading contribution to the Kähler potential is of this type. So we'll be using corrections at different orders in alpha prime and loop. For example, in LVS in the large volume scenario, they use the correction, this correction, which is at order alpha prime cube and tree level in the loops, which occurs at R, which is an R to the fourth correction. And on top of that, we use two more corrections, which are the leading order in potential, which is a moduli definition, which is proportional to the log, which is this alpha log term, which occurs at one loop at alpha prime squared, and another correction, which is this correction, which is at alpha prime cubed and one loop. And this, in the paper, we considered all the known corrections for type 2b string, superstring, that we know in literature, and gave an analysis that only these terms are the leading ones. There are much more, for example, at alpha prime square and one loop. There are much more corrections which turn out to be subleading, and we have done the analysis, I think, in the appendix of the paper. So these are the leading contributors in the Kähler potential. So with this, once we have the Kähler potential, its next job is pretty easy. We compute the scalar potential at F-term scalar potential at leading order. It turns out there are three terms which are the leading terms here, and we get a series of minima where you can have anti-de Sitter minima, de Sitter minima, and the Minkowski minima. And it's easy to see that if alpha, if alpha is positive, you can have a minima at tau equals to exponential c over g s squared, and this would be a de Sitter minima. So yeah, we get a series of minima coming from anti-de Sitter, Minkowski, and de Sitter. So with this, we have fixed the Kähler modulus and using perturbative corrections to the Kähler potential. But in principle, even if, for example, these two corrections are at alpha prime cubed and alpha prime cubed one loop, even if this is a special correction occurring when you have a certain setup of branes, even if this correction is absent, those of us know that the anti-brane uplifting in principle or the T-brane upliftings, these things can also uplift the potential and make it a de Sitter minimum. So we made that comment in the paper as well. With that, I'll move to the brane-antibrane inflation scenario. Once we have the Kähler modulus fixed, the next job is to study the inflationary scenario, which had the eta problem. So in the original setup, I mentioned the when I wrote the eta, it was very hard to get inflation, or it was very hard to have a eta parameter much less than 1 without warping. So, and the moduli stabilization and its mechanism was very important because non-perturbative effects can lead to an eta problem. As you can see from equation 8, if you take two derivatives, it becomes the same order and you have an eta problem. And so a way out is to use the perturbative corrections that I just highlighted. So yeah. So I'll try to quickly sketch how to arrive at the potential for the brane-antibrane inflationary scenario. So the starting point is the action of a D3 brane. You have, for example, the dBi term and the Chern-Simons term. So the origin of the Coulomb potential, which arises when one introduces the back reaction of the D3 brane in the background metric. For example, here in the original paper, I think they computed open string amplitudes between the brane and an antibrane. In this case, I think following the footstep of KKLMMP, we considered the potential for an antibrane and added the D3 in the scenario, which introduces a back reaction effect. And with this, we can compute the potential. So we highlighted two cases, one without working and one with working. So the C0 previously, which I highlighted, is the tension of the brane here, and here the tension times some volume terms. Okay, with this, we have the potential at play. And I have restored Planck units, which which we will use for the inflationary analysis. And with this potential, we can study inflationary scenarios because now the volume mode is stabilized and you do not generate corrections to the eta parameter. So the trick we use is actually when we use Kähler perturbative correction, you stabilize the whole volume. You do not, for non-perturbative correction, we used to stabilize just tau. So the corrections to eta or the influx corrections to eta were still there because we were generating, when we expanded in small phi, we generated a correction to the eta parameter. But when we use non-perturbative corrections, we stabilize the whole combination. So when we use perturbative corrections, we stabilize the whole contribution. So we do not generate corrections to the eta parameter. So in the paper, we used the brane-antibrane, we formulated the brane-antibrane inflation in the nilpotent superfield formalism. It's easy to see that if we do not have this G sigma term, one can work out the F term scalar potential, and this will be the famous anti-brane uplift of KKLT scenario. So in the paper, we did two cases, one where you have G of sigma to be 0, and another case where you have G of sigma to be non-zero. With this, we constructed the inflationary potential in this framework, and which is the same experimentally favored form. And in the two cases we studied, of course, they're different because we had two different cases of G sigma equal to 0 and G sigma not equal to 0, where sigma we are calling the whole combination, tau minus the inflaton square, that is the whole volume. With this, so we connected both the inflationary era and the dark energy dominated era, or the current late time physics, in a consistent fashion, in the sense that we have stabilized the modulus and we have tracked the dependence of the Kähler modulus throughout the evolution from inflation to the current setting. So we can also compare the analysis with data, and we see we have a very small Kähler to tensor ratio, which is within bounds as well, and the spectral index within current bounds as well. So with this, we have a few more things to consider. What are the few things? As I mentioned, we considered this setup in a warped compactification, that is a Klebanov-Strassler compactification, where the antibrane sits at the tip of the throat, and the D3 brane moves towards the antibrane, which is at the tip of the throat. And so in a case of warping, you need the brane or the inflaton, that is the brane separation, to fit within the warped throat if you want eta to be dependent on eta to be a function of the warping, so that you can have a small eta. Also, we encoded some of the effective field theory constraints from literature, like for example, supergravity regime at the tip of the throat requires GSM to be greater than 1 for the stability of the conical modulus. You need this to be greater than 46, although there was, this is a conservative bound because current bounds show that it could be more than the number of antibranes in the setup. Then you have a non-singular bulk condition, that is the throat fitting in the bulk. And with this, we consider the parameter space consisting of both the inflationary constraints and the constraints from effective field theory. And on top of that, forcing the late time minima to be a de Sitter minima. And we get two cases. That is, for one of the cases where you have a linear, when we had a linear contribution, for example, G of sigma to be present, we had we got this parameter space where we plotted W0 against GS. And in this case, the inflationary minima and the late time minima are well separated. That is, after the end of inflation, volume modulus moves to a new minima. And for this, the inflationary minimas are for the volume modulus is a bit, we just observe a small shift in the minima of the two in the second case. So with this, we see that we saw a non-zero parameter space where brane-antibrane inflation can occur with constraints from effective field theory satisfied and in agreement with current bounds. So this is the case with linear contribution. This is the case with no linear contributions. And with that, I'll just summarize what we did in the paper. So we solved the eta problem of brane-antibrane inflation. We are doing some more work at Brac University and at my institution in Czechia, Masaryk University, where we are trying to understand this few things. For example, the alpha prime, how the alpha structure of these perturbative corrections are, and how it affects upon compactification, and more general scenarios where there are eta problem which can be solved by perturbative corrections. And we obtained a 4-dimensional de Sitter using only perturbative corrections to the Kähler potential. So we also connected late time physics and unlate time physics, where we have satisfied the effective field theory and experimental constraint. But the storytelling is not yet complete because we need to consider, for example, the reheating case and full-on construction, where you have, for example, we introduced fluxes, we need explicit Calabi-Yau constructions for this. And in this construction, we kept the tadpole as low as possible, but in general, you need a complete scenario where all of these happen. So I'm a bit early, I guess. Thanks.
Okay, thank you for the nice talk. Any question?